In today's continuing information on light, we are going to look at something called spectroscopy. And I'm going to tell you why we're going to do this is because later in the semester, you're going to be looking at what are called exoplanets. And exoplanets are planets that exist around other suns. And one of the big things in science right now is to look for possible life or possible signs of life on other planets outside our solar system. And so to do that, you have to understand the basics of spectroscopy. And also you can analyze, we talked about yesterday that you can look at nebula and galaxies and things and be able to determine different characteristics based on what wavelengths of the electromagnetic spectrum you're looking in. And that will also help with that. So that's kind of the end goal with this is you will actually be building a model of a probe that you will send to an exoplanet or maybe even to a moon of an exoplanet, and you'll be looking for life, and you'll have to understand the basics of spectroscopy. Okay, so spectroscopy is the study of the absorption mission of light and other electromagnetic radiation. Spectroscopy is a powerful tool used in the scientific disciplines to explore everything from very large to extremely small, from stars to atoms and molecules. So again, we're going to get into the basics of it today. And again, I will give you this sheet once we get back to school, if that ever happens. So just a review from yesterday, electromagnetic radiation, the spectrum of light. Now I want you to notice this one goes in a different order. It goes from high energy to low energy, from small wavelength to large wavelength, but you have to be comfortable going back and forth in that. So again, down here, we have high energy, high frequency, okay, wavelengths. Here we have low energy, much bigger wavelengths. Here we have much smaller wavelengths. So again, gamma, uh, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. What I do want you to notice because we're going to be talking about visible light today, the stuff that we can see because we have receptors for them, that the wavelengths of life go Roy G. Biv. So Roy is red, orange, yellow, green. Biv is blue, indigo, and violet, which you may have learned this previously in your academic career. But what I want you to notice here is that red has a longer wavelength than blue. Okay, so red has less energy, but it also has a longer wavelength, a bigger wavelength from crest to crest. Red is the longest, blue is the smallest wavelength. Okay, so red has a larger wavelength, blue has a smaller wavelength, red has less energy, blue has more energy. Okay. Red has a higher frequency, or sorry, red has a lower frequency, blue has a higher frequency. So that's going to be important for what we're talking about today. Okay. Okay, so what can we do with spectral lines, which will make more sense in a second? We can tell which elements are present. So if we're looking at something that is light years and light years away, remember we've talked about the elements of life, hydrogen, oxygen, we talked about carbon dioxide. We've talked about those basic elements when we talked about water and the atmosphere that we need that obviously helped us have life, but also is going to make a difference in an exoplanet. So we're looking for characteristics on an exoplanets that mimic Earth. We can also tell which direction an object is moving, and I'll go through that. And then we can also tell how fast an object is moving by using spectroscopy and by using the electromagnetic spectrum. Okay, we're going to talk about redshift and blue shift. I will get into this and show you videos of this when we get back, but I just want to go through it now. So just kind of pay attention and see if it can stick with you. Redshift is a visible form of Doppler effect. The Doppler effect is about sound waves, but I want you to think about, this has happened to everyone. Okay, you hear a fire truck, or you hear a police car far away. Okay, and I want you to think about how that sound changes as it gets close to you. Okay, the sound gets louder. The sound gets louder as it gets close to you, and then it comes past you and it's its loudest. And as it goes past you and then goes away from you again, it gets fainter. So what's happening is when it's far away from you, the sound waves are long wavelength sound waves. And as it gets close to you, the sound waves get closer and closer together. The frequency goes up and it sounds louder. And as you move away, the sound waves get longer and longer again. Okay? The same thing happens with light. Okay, the same thing happens with light. So one of the big discoveries about our universe a long time ago was the fact that the universe is expanding, that things are moving away from us. Okay, they are moving away from us. That has been very consistent in science, that things are moving away from us, that the universe is expanding. Now, I will tell you as a side note, the James Webb Space Telescope has kind of put a question mark on that. We know it's moving away from us, but the James Webb, what it has discovered is that it's not moving away from us in a consistent fashion. Depending on what part of the universe you look at, it's expanding at different rates. So that is one of the questions that James Webb has brought up that we need to work on answering. But how does James Webb or any other telescope know that it's moving away from us? Well, there's something called redshift. Okay, redshift. So we talked about sound waves with the Doppler effect. The sound waves, okay, as it gets closer to you, the sound waves get closer and closer together. Okay, it shifts towards an increase or a decrease in wavelength or an increase in frequency. Light waves do the same thing. Okay, so if something is moving away from you in sound waves, the sound wavelength gets bigger. The same thing happens with light. So when a star or a planet or a part of the universe is moving away from us, then what happens is it shifts towards the red. So remember, back to this, red has the longest wavelength. Okay, it has the longest wavelength. So what happens is something is moving away from us, okay, the wavelengths get, so here's close to us, okay, it's close to us, and then as it gets farther away, the wavelengths get bigger or farther apart from each other. The wavelengths increase. So what's going to happen is when you're looking at something in a microscope, or not a microscope, a telescope in the infrared, it's going to appear more red because it's moving away from us. And as those wavelengths increase, we go from the blue side of the visible light towards the red, okay, towards the red. So the James Webb Space Telescope is looking at things from 13 billion years ago, and we'll go into how and why it's doing that. But they appear very red because they're moving away from us and they're very old and they've been moving away from us for a long time, so they appear more red. Okay. If something is coming towards you, okay, from a light standpoint, moving towards you, then it's going to shift towards the blue because the same reason we're getting bigger, but as it gets closer to you, they're going to be, okay, it's moving towards you. The wavelength, just like when the sound comes close to you, the wavelengths, the frequency increases. Same thing, as the frequency increases, we move from the red towards the blue. Okay, so in most cases with astronomy, we're talking about redshift. Okay, we're talking about redshift. It is moving away from us, increasing the wavelength size, decreasing the frequency, and it appears red. Okay, it appears red. We will go over this again, but if you need to listen to this part again, back it up and look at it again. Okay, next we are going to look at spectral line. We're going to try to look at spectral lines. Okay, there we go. Okay, so spectral lines. I'm just going to read this to you, and you can read it on your own, and then I will show you an example. So spectral lines are how we're going to identify if certain elements of the periodic table exist coming from an exoplanet, coming from a star, coming from anything that can emit light. Okay, so a spectral line is a distinct dark or bright line appearing in an otherwise continuous spectrum, representing a narrow range of frequencies where light has been absorbed or emitted. Okay, so absorbed, remember what that means. That means it's taken it in. Okay, light has stopped there. Or emitted, which means to put light out by atoms or molecules, essentially acting as a fingerprint to identify the specific elements present in a source of light, like a star or a gas cloud. So stars or gas clouds emit light. This can be used for exoplanets too. I'm not going to get it. Planets don't emit their own light, but they will reflect light from a sun, and that can actually help us to identify what elements are on the planet. If there is a black line in the visible spectrum, that means the frequency that has been absorbed. Okay? If it is brighter at a frequency, that light has been reflected back. So go back to absorbed. When light hits something and stops at absorbed, reflected means it hits it and then reflects it back. Now, I understand after reading this, it may not make any sense to you, but let's go to the next slide and hopefully it will be a little more clear. Okay, so what spectroscopy can do, we're looking at the visible light spectrum. Okay, we're looking at that segment of the electromagnetic spectrum that we can sense. And so can telescopes, and so can equipment that actually just senses the visible spectrum that sun, or that star, I should say, is emitting. Our sun does it too, that a star is emitting, or that a gas cloud is emitting. So we can detect what visible light is coming off that, let's say, star. Okay. But when we look at that visible spectrum, so this is the blue side all the way to the red side. So here's your Roy G. Biv. Okay. What you will see in a spectral line is you will see an area that may be black. Okay. Now they have the colors here, but imagine this would be black. Okay. So hydrogen puts off the visible light, but hydrogen will have these specific areas of the visible spectrum that will appear black. Okay. Helium in that visible light will have this pattern, okay? And notice these two patterns are different. So this is light that is being absorbed. This is the frequency in the visible spectrum that hydrogen absorbs, okay, here. This is the frequency in the visible spectrum that helium absorbs. And so these detectors will get these spectral lines, okay? So if we are visualizing or we are taking measurements from a young star and you have these areas, okay, you have this fingerprint, we can now determine what elements that star is emitting. Okay, and what you do is you take this and you match it up with this. You look at the lines, okay, you look at the lines that match up. So what we see here is, do we have hydrogen in this star? We go down. Yes, we do. Okay, because all these lines match up. Hydrogen, 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 here and here. So this young star has hydrogen, but it also has more lines. And if you line up all the ones with helium, you will notice that they line up also. So what this tells us is that this star has hydrogen and helium. And that's what most young stars are. Young stars are basically hydrogen that has come together because of the force of gravity and starting to go through fusion and forming helium. Okay, so young stars are hydrogen, helium. So we could actually age this star based on the fact that it has hydrogen and helium. Okay. So again, basically what you're doing is, this is what hydrogen looks like on the visible spectrum. This is what helium looks like. Oxygen has a look to it. Carbon has a look to it, has a fingerprint that goes with it. So if we have carbon dioxide coming from a star or coming from an exoplanet, then we can determine what elements are on that planet. By doing that, if we find a planet that is emitting the spectrum that shows us hydrogen and oxygen, that gives us an idea that there could be water there. And that could tell us that there is life, because where there is water or where there's life, we know that there's water. So we can make a educated guess that that planet has a chance of having life on it. So we'll go through an example of these. And again, this may be something you want to relook at and go through again. It is really interesting. And like I said, when you develop your probe, you're going to have to be able to look through a spectroscope, or you're going to have a spectroscope on that probe in order to detect what's in the soil, what's in the atmosphere, and so on. Okay, so this is a picture of the whole doodle note that I'm going to give you. What I've basically done is gone through each section for you. Again, hopefully to give you more understanding. We will go through these again because I knew these are kind of more difficult concepts, but they are ones that you're going to actually use and apply as we go through the semester. So I hope you're all having a good day, and I will hopefully see you soon.